In this module, we'll be building a Simio model of a serial manufacturing line. You can see the diagram of the line here. It's the turning process followed by a drilling process, a milling process, an inspection, and a packing operation. Note that this problem or this example was a laboratory exam for my undergraduate simulation class. So in this video module, what I'll be doing is building the model as we would have expected the students to do during the lab exam, which lasted about 2.5 hours. So before we start building the model, let's look and see what the assignment actually is. So we can see that parts arrive at the rate of 20 per hour, Poisson arrival process. So we know that means we'll have exponentially distributed in arrival times. The characteristics of each machine, the turning machine has capacity 1 and a triangular distribution. The drilling machine also capacity 1, triangular distribution. The mill and pack both have capacity 2, and finally the inspection has a deterministic processing time of 2.1. Also note that the result of the inspection can be three different outcomes. So parts can either be classified as good, in which case they go to the packing operation, they can be rejected, or they can go back for rework. So some of the components of the model, entities should move from machine to machine instantaneously, so that tells me we want to use connectors. The symbol needs to change colors, so we need to use the symbol list. We want to name the object instances, so for the turning, obviously we want to name the object instance turn, and so on. We need a status plot that plots the average number in system and the instantaneous number in system over time. We have a user-defined statistic that records the number of times that each good part is milled. We have some experimental conditions here, run length of 1,000 hours, warm-up of 500 hours, 25 replications. And finally, we have several different experimental responses that we need to incorporate into the model. Now that we have a good understanding of the assignment, we can start building the Simio model. So I've already started placing some of the components just so I didn't have to place them all at the start of the video. I placed a source and then my 5 servers and 2 sinks because I have a good outcome and a bad outcome. As you recall from the assignment, it said that part entities move from machine to machine instantaneously. So that tells me that I want to use connectors. And so I'm going to connect my source to the first server, my first server to the second server, and so on in serial fashion. Go ahead and get those guys all connected. Server 5, packaging, sync. We also have an outcome of bad, so parts can be bad. And we can also go to rework, where we have to go back to the previous station. There we go. So we have our connectors all included. We'll drag a model entity out. And one of the other requirements on the assignment was to name the objects. So we'll go ahead and do that. We'll name the first one turn. The second station we will name drill. Third station we'll name mill. Fourth station we'll name inspect. Fifth station we'll name pack. And we'll go ahead and name our sinks good and bad to distinguish good parts from bad parts. And we might as well name our default entity also. We'll call this parts. So I have my model set up. I haven't put any parameters in, but I can basically run it and see what happens. And what we expect, since we haven't input any parameters, is for this decision from inspect to be 1/3, 1/3, 1/3, equal probability for each of the outcomes. So we could watch for a while until we're confident that we are actually seeing the behavior we expect, 1/3 outcome each way. I'm pretty satisfied at this point, so I'm going to then stop the model and go back and put some of the parameters in. So let me see if I can shrink my Simio down here so we can actually see. Oops, don't want to do that. I want to be able to see the parameters that we need to do. Not cooperating here. Let's see. There we go. So there's the parameters we need to fill in. Our parts arrive. Let's see if we can see that. The parts at the rate of 20 per hour. So the arrival rate is Poisson, arrival processor's Poisson. So that tells me that I'm going to have exponentially distributed interarrival times with a mean of 3 minutes. So 3 minutes will give me an arrival rate of 20 per hour. Easy enough. Go to the turning station. The parameters are triangular 2, 2.5, and 3. So we have triangular 2, 2.5, and 3, also in minutes. The drilling station, triangular 1, 2, 3. Triangular 1, 2, 3. The mill is triangular 3, 4, 5 and has capacity 2. So it's triangular 3, 4, 5 and has a fixed capacity of 2. The inspect is deterministic 2.1 minutes. Get rid of all of that, 2.1 minutes. And finally, pack has triangular 2, 6, 10, and it also has capacity 2. So we're going to put triangular 2, 6, 10, and capacity 2. Next, we have to do our inspection outcomes, and the outcomes are given here. So we have a probability of 25% that we return to the mill, 70% good, and 5% are rejected. So I'm going to implement that using selection weights. So I will just use those probabilities here and say this is 0.25. The outcome for good is 0.70. And finally, our bad outcome is 0.05. 0.05. So we have a 0.05. Get rid of, let me do this before we continue. Get rid of these arrows. Yeah, there we go. 0.7 and 0.25. So now we don't need to see the assignment anymore. And that is our base model. So now that we have the base model built, the first thing I would want to do in building this model is to do a little bit of verification and make sure that the model is coded as we think it is. And so to do that, I developed a static model. So I used just a queuing model to determine the exact probabilities at steady state. The exact utilizations at steady state. So you can see my model here. I have arrivals of 20, which gives me my inner arrival time of 3, and then I just have my 5 stations across here where I computed the arrival rate, the service rate, and the utilization for each station. Really the only complication here in this problem, let me see if I can draw this out here, is when we go to the mill, and then we have the inspection, and then we have this three-way outcome. So we have packaging, we have bad, and then we have some going back. And so this is a rate of 20. And so we have an arrival rate that we see is greater than 20. So in this case, this was a 0.25 probability. This is a 0.7 probability, and this is 0.05. And so if we do this from a queuing perspective, we can see that the lambda that the mill sees will be equal to 20 over 1 minus 0.25 for the reentrancy here. The rate of departing entities here is going to be 20 times 0.05 over 1 minus 0.25, because we have actually a greater probability of 0.05, greater than 0.05, because entities can loop back. So since they can loop back, we have to account for that there. And then so the arrival rate here will simply be the 20 that came into the mill, 20, minus this rate right here. And so that's what we see in our spreadsheet formula here for pack. And so this tells me my expected utilizations for turn is 0.833, for drill is 0.667, for mill is 0.889, inspect is 0.993, and pack is also 0.993. So I can go back to my model, and let's just make a quick simple run here. I know from our run conditions I'm going to have to run for 1,000 hours. So let's go ahead and just set that run condition there. run the model for a little bit and let's just watch it and make sure it doesn't do anything strange just sort of on face value. So we speed it up quite a bit, watch it for a little while. Everything looks kind of stable here. So we'll go ahead and jump to fast forward and get to our single run, our single replication. There we are at 1,000 hours. And now I can jump into my results, and then let's just drill this down, or let's filter this out to my metric of interest for my verification, which is scheduled utilization. So I just grab those guys. And now we have our single run estimates of our utilization, which we can compare to our static model here. Let me see if I can get this all on the same page. Shrink this guy down a bit. There we go. And so we have for drill 67.9, and we have 0.678 here. For inspect, 93 looks pretty good. Mill is 89, looks pretty good. Pack, 93 looks pretty good. And finally, turn is 83 also. So based on our single run, we have some confidence that our model's correct because we're actually getting those expected values. The last thing we're going to do in this video is implement our experiment. So we go back to our assignment and we see that our experiment has a run length of 1,000 hours, as we said, with a warm-up of 500 hours and 25 replications. So we'll go back to our model, Project Home, create a new experiment. There we go. We have 25 replications that we want. We had already set to 1,000 hours for our run type. So the last thing we have to do is set our warm-up period here to be 500 hours. So we go back here, make that 500, and we are good to go. And we're back now that our experiment is completed. You can see we've done our 25 replications. So we can jump over to the pivot grid and go through the same filtering that we did before. Except let's just go ahead and add the standard queuing metrics that we usually do. So I'm going to do the number in system, scheduled utilization, and finally time in system. If I can get my mouse to cooperate here, time in system right there. And just filter that down so we can see sort of our typical queuing metrics. And then of course we typically don't want to see all the values. We just are interested in the average and then the percent value that we can use for our verification. So there we go, back to percent, and there we go. And we can again, of course, compare these to what our expectation was, and we'll see that our model matches up pretty well, and our confidence interval half widths are pretty good. So at this point, I'm pretty satisfied. One thing I'm going to do is I'm going to add a view here for our pivot grid. Just call this the queuing stuff, so that I can go back in and unfilter as we continue. So that's the end of this video. In the next video, we will continue with the assignment and start implementing the required components for our model.